Hi, in this video, we are going to look at a very useful counting technique. It is the principle of inclusion or exclusion, which we'll also refer to as pi. So according to this method, we are able to count the number of elements of a particular set which satisfies certain properties. So I will just explain the theory first, and then we'll look at some examples by which we learn how to apply this. So let S be a known finite set, and suppose P1, P2 till Pn are n properties related to the elements in S, the elements in S. So basically, the elements of S could have any of these P1, P2, Pn properties. And it is possible for each element to have more than one property also, right? So basically, you can figure out for each element and any property Pi, you can determine whether X has that property or not, right? Let's say the question is find the number of elements in S that do not have any property Pi, where I can go from 1 to n. Okay, so we want to find the number of elements in the set S that do not have any of these properties Pi, where I goes from 1 to n. So this is the way we set up such a problem. So we define Si as the set of X such that X belongs to S and X has property Pi. It's the set of Si is the set of all the elements of the set S which have the property Pi, right? So if I goes from 1 to n, we have different sets like this, S1, S2, Sn, right? So what we need to find, these are all different subsets of our S set, right? If we want to find number of elements in S that do not have any property Pi, we want to take the intersection of S1 complement. S1 complement are elements that don't have property P1. Elements that don't have P1. And similarly, intersection of that with S2 complement, S3 complement, and so on till Sn complement, right? So basically, this set, which is the intersection of all of these sets, is what we want to find out, right? We want to find out the number of elements that do not follow any of those properties, right? So the theorem of inclusion and exclusion gives us a nice way to count this. S1 intersection S2 complement intersection S3 complement intersection Sn complement will be equal to, this is the theorem for inclusion and exclusion, will be equal to mod of S minus summation I goes from 1 to n mod of Si plus summation I1 I2, where 1 is less than I1 I2 less than equal to n. This is Si1 intersection Si2. Basically, it's 2 at a time. These are subsets where it doesn't have property I1 and doesn't have property I2, right? And 2 at a time, if you pick, you are adding those. Then you are subtracting 3 at a time. 1 less than I1, I2, I3 less than equal to n. I1 intersection Si2 intersection Si3, and so on till finally minus 1 power n. It is the minus 1 power n S1 intersection S2 intersection till Sn. So this is what we wanted to find. So the theorem of inclusion and exclusion is saying this. What are we actually doing here? We are taking the total number of elements in the whole set, right? Total number of elements in the whole set. Then we are subtracting all the elements which satisfy one property. These are the one property elements, right? So for example, if I have S1 intersection S2 intersection S3 complement, suppose this is what I wanted to find, I would say this is this mod S minus S1 minus S2 minus S3 one at a time, then plus S1 intersection S2 plus S2 intersection S3 plus S3 intersection S1, and finally minus S1 intersection S2 intersection S3. This is what we are getting. Now think about it. If I draw a Venn diagram, this theorem becomes clearer. So I have these sets. This is my S1, S2, S3, and this is the universal set S. What I want to find is the intersection of the complements of S1, S2, and S3, right? So I want to find all the elements that are outside these sets, right? So basically, that's the same as counting all the elements in the union of these sets and subtracting it from the total number of elements, right? So you should do mod S minus S1 union S2 union S3. And how do I calculate this union? This is what basically what we are doing in this whole portion is, right? In order to calculate the union, we add S1, S2, S3, we subtract the 2 times intersection, the double intersections, and then finally we add a S1 intersection S3 intersection S2, right? The basic idea is you want to count every portion only once. So when you add S1, S2, S3, this portion gets counted 3 times. When you subtract S1, S2, S2, S3, S3, S1 intersections, you are subtracting this portion again 3 times. So it has not been counted at all. So you have to finally add an element here. So basically what I'm saying is that if X belongs to K sets in S1, S2, Sn. What does this mean? X has K properties among these N properties, right? Now, when I count this, suppose I have to find out S1 complement intersection S2 complement intersection Sn complement. I am saying this is like this: mod S minus summation of one at a time each of the SIs, and then plus 2 at a time SI intersection Sj, and so on, till finally minus 1 power n SI intersection S1 intersection S2 till Sn. This is my formula for inclusion and exclusion. Now here X is being counted one time, counted once, because X is an element of the whole set and it will only be counted once if you count the whole set, right? Here, however, X will be counted KC1 equal to K times. Why? Why KC1 times? Because X belongs to K different subsets, right? Here, it will be counted KC2 times, because there are K subsets where X belongs, right? X is a single element X, but it could be a part of multiple subsets, right? S1, S2, S3, it could be a part of K sets like that. So when you take two at a time, this X could belong to two out of those sets. You can say K choose two times, it will appear in these, right? And finally here, it will appear KCK times or equal to one time here, right? When you take the intersection of all of them. So when you are doing the overall count of this term, the RHS, here this is KC0. You are actually counting X how many times? You are counting X KC0 minus KC1 plus KC2 minus KC3 till minus 1 power n power k KCK, which is actually equal to 0 by binomial theorem. So the idea was here we wanted to not count X, right? We wanted to count all the elements that do not have any of these properties, P1 to Pn. So when you do this type of counting here, including and excluding in successive steps, you are basically removing all the times X should appear. You are not really counting X, you are counting elements that do not have any of those properties, right? So the corollary or dual theorem of inclusion and exclusion is basically this: for any subsets S1, S2 till Sn of S, since S1 union S2 union Sn whole complement is equal to S1 complement intersection S2 complement intersection Sn complement, we have, if you wanted to, if you want to add S1 union S2 union Sn plus the number of elements in S1 intersection S2 intersection Sn intersection, that adds up to mod S, right? Because this actually is the complement of this, right? And when you add some set plus its complement, it should be the overall universal set. Therefore, theorem 2 is basically the dual form of pi, which says S1 union S2 union Sn. The count of this would be equal to summation of 1 to I to n Si minus summation 1 I1 I2 less than n Si1 intersection Si2 and so on, alternating signs till minus 1 power n minus 1 S1 intersection S2 intersection Sn. How are we getting this? If you use the first formula, the first formula gives us the way to count this. So using the formula from theorem 1, which was the number of ways to count this, we are just saying this is equal to mod of S minus mod of S1 intersection S2 complements, right? So if you put that there, this is what results. It is all good to know the theory here. The way to apply principle of inclusion and exclusion in problems is what is essential. So now what we'll do is we'll look at some examples that will explain this concept much better. So a simple, very simple question, the typical question or for this type is, find the number of positive integers. Find the number of positive integers less than 1000 which are neither divisible by 5, which are neither divisible by 5 nor by 7, nor by 7. Okay, so the key thing in inclusion and exclusion is always to set up your sets and your properties very clearly. If you set up the symbolism right, then half the problem is very easy. It's very easy to apply the theorem if you know what you're doing. So we are going to say S is the set of integers less than 1000. Sk are set of integers divisible by k. Set of integers divisible by k. So what we need in the problem is integers not divisible by 5, not divisible by 7. So we need S5 complement, the set of integers not divisible by 5, intersection with S7 complement, and we need the number of elements of this set, right? So this is straightforward application of theorem 1. So this will be mod of S minus S5 minus S7 plus 2 at a time intersection, right? So this is it. So now we just count the individual sets. The total set of integers less than 1000 is 999. The integers less than 1000 which are divisible by 5 will be GIF of 999 by 5. The integers less than 1000 divisible by 7 will be GIF of 997 by 7. And finally, the integers which are both divisible by 5 and 7 would be the integers which are divisible by 35. So that will be 999 by 35 GIF. And if you evaluate this, it will come out to be 686. And that is the answer. That is the number of integers that are neither divisible by 5 nor divisible by 7. Right? Let's look at another problem. Question number 2. We have this question. Use the digits 1, 2, 3 to construct n-digit numbers. To construct n-digit numbers so that all the digits 1, 2, and 3, all the digits 1, 2, and 3 appear at least once, in an n-digit number, Find the number of such n-digit numbers. Find the number of such n-digit numbers. So each of the digits 1, 2, and 3 should appear at least once, right? Okay. So let's set up the symbolism for it. S is the set of all n-digit numbers formed using 1, 2, and 3, right? And let's define the set Sk to be all x such that x belongs to the set S, but there is no digit k in x. And k can be basically 1, 2, or 3, right? There are only 3 digits available to us. So we are going to design a set Sk such that it is a number using these digits in the set S, but it doesn't contain one particular digit, which is k. So basically, what is S1? It is the set of all n-digit numbers which don't have 2 or which don't have 1, which are formed using just 2 and 3. Similarly, S2 will be the set of all n-digit numbers formed using just 1 and 3. They don't have 2. And similarly, S3 doesn't have 3, right? Now, what is the number of elements in this set? Mod of S would be equal to, for each of the n digits, there are 3 options here, 1, 2, or 3. So it is simply 3 power n, right? And mod of Sk would be 2 power n, because here k can be 1, 2, or 3. In each case, what happens? One of the digits is not allowed, right? So you have only 2 choices for each step. Now, if want to find out what is SK intersection SL. When two different letters are not allowed, then you have only one digit left, right? K and L, two different letters are not allowed, so the intersection of this will be simply 1 because there is only one type of number that you can form. So let's say, for example, S2 intersection S3. You can only form 1, 1, 1 n times. That is the only number, right? Because you can't use 2, you can't use 3, right? So for all K and L being from 1 to 3, intersection of SK and SL will give you one element, right? Great. And similarly, S1 or SK intersection SL intersection SM would be 0. If all three digits are not allowed, you can't make a number, right? So what we need in the question, think about it. What we need in the question is you have to use at least once every digit, right? All of 1, 2, and 3. So you can't have S1, right? S1 basically had 1 missing, S2 had 2 missing, S3 had 3 missing. So you need S1 complement, intersection with S2 complement, intersection with S3 complement. This is what you are trying to find, the number of elements in this set, right? Because this has at least one time 1, and this has 2, and this has 3 at least once, right? So if this is what we want to find by theorem of inclusion and exclusion, we write it like this: mod S minus mod S1 plus mod S2 plus mod S3 plus mod S1 intersection S2 plus S2 intersection S3 plus S3 intersection S1, and finally minus S1 intersection S2 intersection S3. This is my theorem of inclusion and exclusion. There are 3 terms with 2 at a time and 1 term with 3 at a time. And this is simply 3 power n minus 3 times 2 power n plus 3. That is your answer for this question, right? Let's look at another example. Notice in all of the problems, the key thing is to set up the question properly, is to set up the equation correctly. If you are able to set up the equation properly on the variables properly, basically, then you will be able to solve the question better. So set up the notation correctly in the beginning. So this question says there are 100 math questions solved by 3 people, A, B, and C. 3 people, A, B, C, and each of them solves exactly 60 questions. 100 questions were solved by A, B, and C, and each person is solving exactly 60 questions. The questions that are solved by all 3 are easy questions, are called easy questions, and the questions that are only solved by one of the persons, that are only solved by one person out of A, B, and C, are known as hard questions. What you need to figure out is which number is higher. Is hard questions, number of hard questions, greater than number of easy questions or not? That is what we need to figure out, right? Again, we'll set up the problem like this. Let's say A is the A, B, C set of questions solved by A, set of questions solved by people A, B, C respectively, right? Okay, so what we know already from the statement is mod of A and mod of B and mod of C, which is the number of elements in ABC set, is 60, right? We also know that the total 100 questions were solved by all three people. So we know that union of A union B union C, the modulus of that is 100. The cardinality of that set is 100, right? Now, if you use the dual form of inclusion and exclusion principle, the union form, so you'll say this should be equal to mod A plus mod B plus mod C minus mod of A intersection B minus B intersection C minus C intersection A plus A intersection B intersection C, right? Now, using the fact that this is equal to 100 and this is equal to 60 plus 60 plus 60, 180, what we conclude from here is mod of A intersection B plus B intersection C plus C intersection A minus A intersection B intersection C is equal to 80. This is my first result. Keep this result in mind. We are using the data of the problem to just figure out the value of this equality. This is an identity that is true. Now we go to the next screen and we'll continue. We'll say let alpha be the number of questions, solved by A alone, A only, right? So think about it. This is my set A, B, C, A, B, C. If you want to count alpha, alpha is the number of questions that were solved by A only. How do we count that? What we can say is alpha should be A minus, you should subtract the A intersection B portion, and you should also subtract the A intersection C portion. A intersection C portion. But notice that in subtracting these, you have correctly subtracted these elements once each, but you have subtracted this portion twice. You don't want to subtract the same thing twice because it was present only once in this set, right? So you need to add A intersection B intersection C to ensure that you are only deleting these elements once, not more than once. You don't want to double subtract instead of subtracting once, right? So alpha is this. Similarly, beta will be B minus B intersection A minus B intersection C plus A intersection B intersection C. This is the number of questions solved by B alone. Questions solved by B only, right? And similarly, gamma is C minus C intersection A minus B intersection C plus A intersection B intersection C. So this is the number of questions solved by C alone. So alpha plus beta plus gamma is the total number of questions that are solved by only one person each, which is basically the number of hard questions, right? And that comes out to be mod of A plus mod of B plus mod of C minus 2 times mod of A intersection B plus B intersection C plus C intersection A, and there is the plus 2 times, actually there is a plus 3 times A intersection B intersection C, right? Now this is the total number of hard questions. We know that this value is 180, and from the first result that we had gotten, that was telling us that A intersection B plus B intersection C plus C intersection A minus A intersection B intersection C was equal to 80, right? Notice that there is minus 2 plus 3. So we can say minus 2 common, and we can write it as A intersection B plus B intersection C plus C intersection A and minus 2 times A intersection B intersection C, and we still have to add a plus A intersection B intersection C, right? Because here there was plus 3, I need only plus 2 here to make this, right? And now this is becoming basically 180 minus 2 times, this is 80 using this result. This whole bracket is 80 plus A intersection B intersection C, right? So we are getting 20 plus A intersection B intersection C is equal to alpha plus beta plus gamma. Now think about it. A intersection B intersection C is the set of questions that are solved by all three. So those are the easy questions. And from here we are getting that the hard questions is 20 more than the easy question. So the answer to the question is yes, the number of difficult questions is 20 more than the number of easy questions. Okay. So that was another application of inclusion and exclusion. We look at the next problem, which is to find the number of derangements of the set 1 to n. So what is a derangement? A derangement is basically a permutation of this set. Right now, these numbers are arranged in a particular way so that 1 is in the first position, 2 is in the second position, and n is in the nth position. These are the correct positions of these elements. When you do a derangement, you are basically rearranging or getting a new permutation of the set such that none of the elements of the set are in their correct position. Are in the correct position. So basically that is the idea of derangements of a set. What you need to count is the total number of derangements. So let's do it by inclusion and exclusion principle again. Let S be the set of all permutations. Set of all permutations of 1 to n. So obviously from here we know that mod of S or cardinality of S is n factorial, right? Then let Sk be the set of permutations. Set of permutations A1, A2 till An which satisfy the condition A of k is equal to k. So basically what this says is that k is in the correct position here. The element k from 1 to n is in the correct position. So Sk is the set of all such possibilities. So it is obvious that mod of Sk, k is in the correct position and the remaining can be in any position. So it will be simply n minus 1 factorial, right? So similarly, if you have multiple numbers in their correct position, if I want to find out intersection of Si1, I2 till Sik, mod of this, that means basically all of these numbers I1, I2, Ik, all of them are in their correct positions. So the remaining n minus k will be in any order, right? So you can find n minus k factorial arrangements to be the modulus of this. So now the number of derangements, when we calculate dn, what we are trying to do is do S1 S1 complement intersection S2 complement till Sn complement. This is what we are counting. S1 was the set where first element was in the correct position. S1 complement is the set where first element is not in its correct position. Similarly, second element is not in its correct position and all the elements are not in their correct positions. That is what we are trying to achieve here, right? So if we want to count this is a direct application of principle of inclusion and exclusion. So dn is equal to S1 complement intersection S2 complement intersection Sk complement will be equal to mod of S minus sum of the terms taken one at a time, 1 to n, Si plus 2 at a time terms, nc2 n minus 2 factorial Why NC2? When you have terms like S1 intersection S2, how many such terms are there? The number of such terms is basically out of the n sets, n subsets. This is till Sn. We are selecting any two, right? NC2 terms. Here, the number of such terms is obviously NC1. So you have mod S minus NC1 n minus 1 factorial plus NC2 n minus 2 factorial and so on till finally you will get minus 1 power n NCn n minus n factorial, right? Which is going to be equal to 1. Now, this mod S is n factorial. So finally you get n factorial minus NC1 n minus 1 factorial plus NC2 n minus 2 factorial and so on till the end here. And if you take n factorial common, you will get 1 minus 1 by 1 factorial, which is equal to 0, plus 1 by 2 factorial, minus 1 by 3 factorial, and so on, till minus 1 power n, 1 by n factorial. This becomes equal to your the number of derangements of the set 1 to n, right? Okay. Now, in the next problem, we'll look at another application of inclusion and exclusion, but this time we'll find the number of functions. So we are saying let x and y be two sets of n and m elements respectively. N and m elements respectively. Now find the number of onto functions. Find the number of onto functions or surjections from x to y. Find the number of surjections. So let's say y set was this y1, y2 till ym, right? Here I goes from 1 to m. Let S of I denote the set of all mappings, from x to y that do not take the value y, do not take the value yi. What does this mean? You have two sets like this. This is y1, y2, ym. Now, if one of them is not being taken, right? S of I is the set of mappings from x to y that do not take the value yi, right? That will mean that S of I, those mappings in S of I are not onto functions, because in onto functions, you are supposed to take all possible values, right? So finally, at the end, we will find out the conjugate or complement of S of I, right? So how many such functions are possible? Think about the total number of functions that are possible here. So if yi is not taken, you have m minus 1 values left, right? If m minus 1 values are left, and here there are n inputs, each input can take any of these values. So the number of functions available will be mod of S of I would be m minus 1 power n, right? Correct. Similarly, if you have Si intersection Sj, that means both yi and yj are not taken, right? So the number of functions that are available in this case, Si intersection Sj, would be there are m minus 2 remaining output values and n input values. So each input can go to m minus 2 places. So you have m minus 2 power n here, right? And now what is the total number of mappings from x to y? For each input n, there are m choices, right? So the total number of mappings is basically m into m into m n times. So it is m power n, right? This is the total number of mappings. Now, basically, we have to compute the value of in cardinality of S1 complement intersection S2 complement, so on till Sn complement, Sm complement. Because we had defined Si where I goes from 1 to M, right? Because there are M elements in the Y codomain set, right? So each Si is saying that one of those elements is not picked up as an output, right? So we don't want that situation to happen. So we are taking complements of this. This is what we need to calculate. By inclusion exclusion principle, this will be this minus all the different ways in which only one term can, one at a time you will take the term. So that will be MC1, which is basically M terms, and mod of SI, right? And then it will take two at a time. So MC2 mod of SI intersection SJ, right? And so on. So this will become basically M power n minus MC1. This is M minus 1 power n plus MC2. This is M minus 2 power n. And so on till finally you will come to minus 1 power M minus 1 MCM minus 1, right? So basically, actually you'll go on till the mth term, right? So it will become MCM finally. So the total number of surjections, these are the number of mappings, will be summation k goes from 0 to m minus 1 part k mck m minus k to the power n, right? This notice that 1, 2, the next time we'll have m minus 3 and so on. So this is the total number of surjections possible or onto functions possible from the two sets. And that's the direct application of your inclusion and exclusion principle, right? Okay. Now, what we look at now is one last problem for this property. And this is this question. Find the number of ordered integer solutions of x1 plus x2 plus x3 plus x4 equal to 20 that satisfy the conditions. And the conditions that are given are 1 is less than equal to x1 is less than equal to 6, 0 is less than equal to x2 is less than equal to 7, 4 is less than equal to x3 is less than equal to 8, and 2 is less than equal to x4 is less than equal to 6. Now we have seen similar questions before, but earlier always our conditions were just one-sided inequalities. We had x1 greater than 1, x2 greater than 0, and so on. That is very easy to solve because you just change the variable, right? However, in this case, what happens here is more complicated. So first step is basically removing this side, the easy side. So we'll say you will make the substitution y1 is equal to x1 minus 1, y2 is equal to x2 is same because it starts from 0, y3 is equal to x3 minus 4, and y4 is equal to x4 minus 2. And now the initial equation from x1 plus x2 plus x3 plus x4 is 20. The equation becomes y1 plus y2 plus y3 plus y4 is equal to 13. And the conditions have now changed, and it is 0 is less than y1 is less than equal to 5, and 0 is less than equal to y2 is less than equal to 7, and 0 is less than y3 is less than equal to 4, and 0 is less than y4 is less than equal to 4 again, right? These are the conditions now, and we have to find the number of solutions of this equation. We have removed the other condition by changing the variable a little bit. Lower bound has been removed, right? Now let's work with this equation and we'll go on to the next screen. So we'll say let S be the set of non-negative integer solutions of which equation? This equation, y1 plus y2 plus y3 plus y4 equal to 13 under the conditions 0 is less than equal to y1 is less than 5, 0 is less than y2 is less than equal to 7, 0 is less than y3 is less than equal to 4, and 0 is less than y4 is less than equal to 4. Under these conditions, we are saying the set of non-negative integer solutions which satisfy these conditions is S, right? Let's say we have four subsets, S1, S2, S3, and S4. And what is S1? Is the set of solutions where y1 is greater than 5, right? Basically, y1 should start from 6 here. y1 is greater than 5. So we are taking the complement of this case, right? The complement of this case. S2 is what? y2 is greater than 7. S3 is y3 is greater than 4. And S4 is y4 is greater than 4, right? So the required solutions for us, required solutions is basically S1 complement intersection S2 complement intersection S3 complement intersection S4 complement, right? This is what we want to find right now. So that is a standard expression for inclusion and exclusion. So now we'll do the actual counting of different cases. So if you do the basic equation here, mod S without any restrictions, is the mod S set, universal set, without worrying about these cases. So that will be basically 13 plus 3C3, 16C3, right? So that becomes your 560 here. That is the first step, because here you will write this first. Then you have to subtract each of them one at a time, right? Minus mod S1, minus mod S2, minus mod S3, minus mod S4. So you will need to count each of these individually, right? So think about it. So if I want to find mod of S1, the number of solutions where y1 is greater than 5. So look at this equation and put y1 equal to 6 there, right? It starts from 6. So change the variable slightly. The variable becomes y1 dash plus y2 plus y3 plus y4, right? And you have already put 6 here. So this becomes 7. And the number of solutions will be 10C3 here by stars and bars method. 10C3 and 10C3 value is 120. So that is your S1. So you start with 560 minus 120. Similarly, S2. For S2, you should do it yourself. S2 will be the number of solutions where y2 is greater than 7. So you have to put already y2 should be 8, right? If you put y2 8 here, it will become 8 will be subtracted. So it will become 5 here. So it will be 5 plus 3 C3. So this is 8C3, right? So 8C3 is 56. Similarly, S3 will be when y3 is greater than 4. So you should put y3 as 5. You will be 11C3 will come. So S3 will be 165. And similarly here also 165, right? But we are not done. We have some way to go yet. We have to remove all, we have to now add the cases where two of these things are happening at the same time, right? We will say here plus S1 intersection S2 plus S1 intersection S3 plus S1 intersection S4 plus S2 intersection S4 plus S2 intersection S3 and finally plus S3 intersection S4. So we have to count these cases now. S1 intersection S2 means y1 should be greater than 5 and y2 should be greater than 7, right? Now, if you think about it, y1 if you put as 6 and y2 if you put as 8, the number of possibilities there is 0, right? Because 6 and 8 is 14, so there is no solution possible for this, right? But S1 intersection S3 is when y1 is greater than 5 and y3 is greater than 4. So y1 you will put as 6 and this you will put as 5. You'll get 11 gone from here. So it will be 2 And finally, you have 2 plus 3, 5C3. So this will be 5C3, right? Which is basically 10. S1 and S4 will be what? Y1 should be greater than 5 and Y4 should be greater than 4. So that will be 6 and 5, 11. So 2 is left, 2 plus 3, 5C3 again, right? So this is also 5C3 for 10 solutions. And S2 and S4 and S2 and S3 both will have same number of solutions, because here it is 8 and S3 is 5, 8 plus 5, 13. So it is 0. So 0 plus 3, 3C3. So 1 and 1 solutions. And finally, S3 and S4. S3 and S4 both are given 5 and 5. So you have 3 left. So 3 plus 3, 6C3. That is 15. 6C3 is actually 20, I think. 6 factorial by 3 factorial, 3 factorial. So that is 6 into 5 into 4 by 6. So yeah, 20. 20 here. And now think about it. Is it possible for 3 of the conditions to be true? No. Technically, in the formula, you have to still subtract S1 intersection S2 intersection S3, but 3 of these conditions cannot be true at once. In no case will that happen. So all of these terms will be 0. So finally, your answer will be 560 minus 120 minus 56 minus 330 plus 5C3 is 10 plus 10 plus 2 plus 20, right? So this becomes 440 minus 330, so that is 110 minus 56 will be 54 plus 40, which will be 94 plus 2, 96. So we are getting 96 possible solutions, and we have learned now how to solve a situation where you have multiple bounds, both upper and lower bounds to our variables. How to find the integer solutions of that case, right? So usually in the stars and bars method, we know how to solve questions where there is only a lower bound. But with principle of inclusion and exclusion, we can solve even other types of questions where there is upper and lower bound. Hopefully you have learned something from this video. The principle is super important. You need to go through the first 15-20 minutes where we explain the theory and try to work out these problems yourself. Once you do 5-10 questions, you should get the hang of it. And you can look through the assignments that I'll be sharing in the course and go through more problems for inclusion and exclusion there. So that's all for this video. We'll continue in the next class.